In this video, I will discuss another important tools that we can use to understand more about acid and base reaction and being able to determine acid and base reaction. So in an acid and base reaction, essentially what we have is that two substances are competing to bond to the proton. And that is another new perspective right there in an acid and base reaction, the fighting over the proton between two substances. And the proton, or the hydrogen, would basically go or bond to the atom that one is more. And that is basically how this reaction will proceed. It will proceed in which the hydrogen will be bonded to the substance that wanted more. And therefore, we want to know what substance or which substance wants the proton more. And that exactly the value to pKa. pKa value tell us, and now it tells us quantitatively, so which is very powerful, that how much a substance wants the proton. And therefore, this is so useful in predicting the product of an acid and base reaction. So first, what is a pKa value? A pKa value is basically a value that can be used to describe how much an atom wants a proton. So every atom that is bonded to a hydrogen has a unique pKa value that describes its affinity for the proton. And we can define the pKa value as follows. The potential, a value that corresponds to the potential or the affinity of an atom in holding on to its proton. And this pKa value can range anywhere between -10 to 50, and it is a measure of acidity. So the stronger the acid, then the lower the pKa value would be, versus the weaker the acid, then the higher the pKa value would be. Okay, and so basically low pKa basically means that the substance has low potential to hold on to the proton, and that would then mean that it's more willing to donate the proton. And that is the very definite definition of what an acid is. An acid is a proton donor. So if something is more willing to donate the proton, that would then make it a stronger acid. Versus if we were to have a substance with a high pKa value for the proton, it means it has higher potential to hold on to the proton or have higher affinity for the proton, and therefore it would then be less willing to donate the proton. And that would then make it a weaker acid. So that's how we can use pKa to determine the strength of an acid. The lower the pKa, the stronger the acid would be. And the higher the pKa, the weaker the acid. pKa value can be used as a quantitative tool in determining electron stability. And the stronger the pKa of an acid, the more stable its conjugates would be. So the stronger the acid, the lower pKa value. And the lower pKa value, the more stable its conjugate base would be. So what this is saying is following. As an acid is giving up a proton, it will then become a conjugate base. So this is the conjugate base. And so if this acid right here were to have a low pKa value for this proton, then the more stable this conjugate base would be. And this is a very powerful tool that allows us to now quantitatively describe the stability of the conjugate base. For an example, let's compare the stability of the conjugate base from HCl and water. So in HCl, this pKa value right here, when we look it up, equal to -7. So this means HCl can give up this proton right here quite easily. So it would then take the electron to it and give up this hydrogen right here as a proton and becomes the following. Become the chloride and the hydrogen ion. And because this EA has a low pKa value, this basically means that this conjugate base right here would then be stable. And now when we compare this with water, so here in the case of water, water has two hydrogen, in which one of this hydrogen right here can be given up as a proton. And again, it does the same thing. This oxygen right here take the electron to it and give up this hydrogen right here as a proton. So we will have the following: hydroxide and the proton. And because this pKa right here in water equal to 15.7, which is much higher than -7 of what we see from HCl. So this basically tells us that this conjugate base right here is not as stable compared to the chloride, which is the conjugate base from a much stronger acid. So that's how we can actually use pKa's as a quantitative tool for electron stability. Now we are able to see that in this case right here, this is much more stable compared to this. So the chloride is much more stable compared to the hydroxide. And this is also consistent with the assessment that we would make using aerial as well. From aerial, we will then see because chloride is a bigger atoms, and therefore we can handle the negative charge better. So this is also supported and consistent with the assessment from aerial. So again, pK value is basically a quantitative tools that allow us to determine the stability between the two conjugate base. And the conjugate base from the acid that have lower pK will then be more stable. And as we previously mentioned, to compare the electron stability of any two substances, we can compare the pKa of the conjugate acid and the substance in which its conjugate acid has a lower pK value is then more stable. For an example, let's say we given these two different species right here with electron on them. So which of this substance will then have a more stable electrons? And now we are given this in the negative form. So this basically we are given this as the conjugate base right here. So therefore we need to convert this into its acid, into its conjugate acid. The conjugate acid of acetate. And we can find the conjugate acid by basically giving a proton to this substance to form its bond. So in this case right here, when we give a proton to this would become acetic acid. And that would be conjugate acid. And the conjugate acid of hydroxide, again, by giving a proton to this would then become water. And now, to determine the stability between acetate and hydroxide, we can now compare the pKa of a conjugate acid. And this is what they will be. The conjugate acid of acetic acid. So this has a pK value equal to 4.75. And this pK value from water is then 15.7. So we will then see that this acetic acid right here has a lower pK value. And that basically means its conjugate base, which is acetate, would then be more stable. So that's how we can determine between acetate and hydroxide, which one is more stable. And again, because the conjugate acid of acetate is acetic acid that had lower pKa compared to the conjugate acid of hydroxide, that is water. So therefore, this would then be more stable. And this is also very much consistent with the assessment from aerial as well, because from aerial we would then see that this should be more stable, because the electron, when the electron locate on the oxygen, it would then be resonance stabilized, and therefore is more stable. But when we use pKa value, we get a very similar answer, except now we have a quantitative tool. And now let's try another example. When the electron locate in acetone versus the electron in water, which of the substance has a more stable set of electrons? And again, we can do this by finding the conjugate acids of these two substances and compare the pKa. So the conjugate acid of acetone will be this substance. And the conjugate acid of water would then be hydronium ion. This pKa value right here, when we look it up, this equal to negative 2.9 versus the pKa of hydronium ion is then negative 1.75. So here in this case right here, we will then see this has a lower pKa. So this conjugate acid have a lower pKa, meaning that this base right here will then be more stable than this base. So now we know that the electron on acetone is basically more stable than the electron from water. And this is also consistent with the assessment from aerial as well, because the lone pair of electron in acetone locate on an sp2 orbital, versus the lone pair of electron in water locate on an sp3 orbital, and therefore this is more stable. And below are some of the common pKa value that we highly recommend students are familiar with to succeed in organic chemistry. And so let's go over this pKa table to make sure you know how to use it. So basically, again, the hydrogen being highlighted in red, so that is the acidic proton right here. So basically, this pKa right here describes how much this substance right here wants to hold on to a proton. And the pKa value for this is negative 9. And this is sulfuric acid. So we can see sulfuric acid is a strong acid, meaning it can gulp up this hydrogen right here as a proton quite easily. And therefore, its pKa is negative 9. And now please note it, and then we move on. And the conjugate base that will then get produced from sulfuric acid will then be hydrogen sulfate. And now, because this acid right here has a low pKa, its conjugate base will then become more stable. And this is why that if we were to rank all of this will be the strongest acid. The strongest acid have the most stable conjugate base. And here are some of the other pKa values. And we will continue to discuss this in this class. And this is an example of pKa values and the format that will be given to students on quizzes and exam. And for a more complete list of pKa value involving more functional group and organic molecule, you can Google Evan pKa table, which will give you a very comprehensive list of pKa values.